Okay, we are going to continue our discussion on equilibrium, and we're going to actually pick up maybe a little bit. I think we'll start right here after we talked about concentration. So I know in both the morning and the afternoon sections we defined term concentration and a couple of different ways we communicate concentration as a weight volume percent or as a molarity. And we did that because to fully understand equilibrium and to calculate an equilibrium constant, which is where we're headed, we needed to know what the term concentration means. So now that we've defined concentration, I want to show you how to calculate what we're going to call an equilibrium constant, okay? Equilibrium constant, which we're going to denote as K. But let's say that we have some reaction. A plus B makes M plus N. A and B, your reactants, M and N are your products. Your lowercase letters, let's say these are the coefficients. And the capital letters, let's say these are your chemical formulas. All right. The way you calculate an equilibrium constant, and I will tell you in just a minute what an equilibrium constant does and why it's useful. The way you calculate it is if you slide over here, it is kind of a factor here. You have a numerator and a denominator, and on top we're going to plug in the concentrations of the products shown in red, so M and N. And by the way, when you have something in brackets, brackets denote concentration. And here we are going to use units of molarity, okay? Remember, molarity is moles of solute per liter of solution. So we're going to use molarity for concentration. Back to the equation though. K, the equilibrium constant, equals the concentration of the products, and they're each raised, if you'll notice, to the power of, or you plug in as an exponent, the coefficient. Okay, that is the lowercase m, n, and then even on the bottom, you plug in the reactant concentrations. They as well are raised to the power of their coefficient. All right. Now, what does K mean? Why is K important? An equilibrium constant. I don't know why. I should have an equation here. There it is. An equilibrium constant, so K is the EQ. Equilibrium constant. And it is a number we can determine that's going to tell us about the ratio of the concentration of reactants to the ratio of the concentration of the products at equilibrium. Here's what that means. That's fancy words for at equilibrium. Do we have a lot of reactants or do we have a lot of products? What are the conditions? Okay, when things reach equilibrium, and somebody brought this up in lecture, I can't remember if it was morning or afternoon. Somebody said, isn't equilibrium something that's always reached? For any system that can reach equilibrium, any reversible system, some reactions and some processes are simply non-reversible in nature. Okay, but for any system that can reach equilibrium, yes, it will. And at equilibrium, it's helpful to know, did the reaction make all or most products? Did the reaction make maybe equal products and equal reactants? Or did it, at equilibrium, do we just have a lot of our reactants and very little products? Okay, that's what K will tell us, and I'll show you how in just a minute. K also tells us, point number 2 about K, it tells us whether the forward or reverse reaction is more favorable, okay? And again, I'll go into that a little bit more in depth in a couple of slides. But if the forward reaction is more favorable, then at equilibrium we will have more or a higher concentration of products. If the reverse reaction is the favored reaction, we will have at equilibrium more or a higher concentration of reactants. I don't know if this is happening to you guys, but I have a figure here on this screen and it's not showing up for some reason. Let me try to scroll back up. I wanted to talk about this. Well, I'll skip over that figure because I can't get it to show up on this video. But there should be some sort of reaction right here. I'll just write it in. It's 2SO2 gas plus O2 gas, reversible arrows, 2SO3, and that's a gas. If we were to write the expression K for this, the way you do that is K equals, as an example here, the concentration at equilibrium of SO3 raised to the second power, because that's its coefficient. On bottom, we're going to have the equilibrium concentration of SO2, one reactant, squared, because that's its coefficient, times the equilibrium concentration of oxygen. The coefficient there is 1, so we don't raise it to a power. So that's an example. I want to make a note here, and I don't think I mentioned this in lecture today, but in our equilibrium expression, we only, I don't know what is happening to this slide down here. In our equilibrium expression, we do not put in reactants or products that are solid state of matter or liquid state of matter, okay? We only put things into the equation for K that are gases, okay? These are all gases. Or we can also put in things that are, so we'll put in gases can go into K, the equation for K, and things that are aqueous, AQ, can go into the equation for K, okay? These two things can, but solids and liquids cannot, okay? I usually get a big question on why that is, and your textbook explains it a little bit better, more in depth. But solids and liquids, as you shift in equilibrium, the concentrations are not changing the way things for gases and things that are aqueous are. So anyways, just as a rule of thumb, you do not put in solids and liquids. You only put in gases and things that are aqueous, okay? All right. I want to move on to this next slide. And let's say we have two experiments. That's what this slide is showing. Let's say we have two experiments with this equation right here, SO2 and oxygen making SO3. Let's say for the first experiment that we start with all reactants. Look at this. We have some arbitrary concentration of SO2 and O2, but we have no SO3, zero SO3. So we're approaching this experiment from this direction. We're going to start with all reactants, okay? That's what's happening. All reactants. No products, starting out. Okay, and if this is our starting point, at equilibrium, here's what we find. At equilibrium, we have these concentrations, okay, units, capital M, this is units of molarity. Let's say we have these concentrations of everything. I don't know if what is happening to this iPad? Well, that's crazy. Please show up. Let me try to go out of it. Maybe the app just needs to be closed. Okay, open it back up. Nope. Let me try to get rid of it. And now reopen it. This is bizarre. Now it's treating my finger like the pencil. Well, I don't, surely you understand what I'm seeing. It's just these crazy numbers and symbols. This has never happened before. Why is this happening? This iPad is something right now. Does it happen if I go to the other one? No. Alright, we're just going to pick up with this other slide. So fast forward through what just happened. Sorry about that. I don't know what's going on. But this is the slide we were on. And I'm just going to pick up talking about this equation. Okay, so we said if we're starting with experiment 1, we're starting with all reactants and no products. And if we're approaching it that way from this direction, all reactants, no products at equilibrium, here's the concentrations for everything that we have. If we were to write K, an equilibrium equation or constant expression for this reaction, we would simply plug in those concentrations in their appropriate spots. So on top, you always put products. SO3 is our only product, and we're going to square it because it has a coefficient of 2. And it's a gas, okay, so we can put it in the equation. 0.938 molar, square that. On bottom, we're going to have SO2. Concentration is 0.062 molar, and we're also going to square that, times the concentration of oxygen, which is 0.538 molar. Okay? And if you plug all this into your calculator appropriately, what you'll find down here is it says experiment 1, K is 425. Alright? Now, if you read experiment 2, it says start with 1 molar SO3. What that means, essentially, is we are approaching the reaction from this end. We're going to start with all products. We're going to put that in our test tube and just see what happens. Well, what can happen is that SO3 can, if you're following the arrow this way, can decompose into SO2 and O2. And at equilibrium, if we let that run to reach equilibrium, here's the concentrations we would find. Okay? So essentially we have here we're starting with all products, no reactants. So I just want to prove to you if we approach this equation up here from 2 different directions, what are we going to find at equilibrium? Okay, so we plug these concentrations in. K equals, on top the products, 0.850 molar, square that, and on the bottom 0.15 molar, square that, because it's SO2, times the concentration of oxygen, 0.0751 molar. If you were to plug all these numbers correctly into your calculator, you'd find that K equals 428. Now I know these numbers are not exactly identical, but they are pretty close. And remember that every experiment, because it's run by humans, even stuff that uses equipment and instruments, there is some experimental error. So these 2 numbers right here are close enough within experimental error for us to say K here is a constant. So it's just some examples of how we would take concentrations at equilibrium, plug them into K, calculate a K, and we've proved here, even if we approach the equation from 2 different directions, that K is a constant. Now, what does K mean? How does it tell us about the ratio of reactants or products? This slide will explain that to us. So we have these color-coded statements right here, and we're going to see how they correspond to this arrow down below. So I'm just going to read the first one, the one in blue. It says if K is a number that is greater than 1, all right? If K is a number, so for example, 425, 428, if K is a number that is greater than 1 at equilibrium, what that means is the concentration of the products is greater than the concentration of the reactants. The forward reaction is therefore the one that is more favorable. You're going to have a higher concentration of products than reactants. And that corresponds to this section of the arrow right here. If K is essentially any number between 1 and 10 to the power of 3, which is 1,000, okay? If K is a number between 1 and 1,000 at equilibrium, okay? This is all at equilibrium. You're going to have more products than reactants. All right? Now, If we read the purple statement, if K is much, much greater than 1, the reaction goes to completion. And still, it's that the forward reaction is favorable. Okay? Go to completion means you're essentially going to have all products. All right? I can write that. Essentially, you're going to have all products. Very little reactants, mostly all products. That corresponds to this purple portion of the arrow, okay? If K is a very, very large number, greater than 1,000, the reaction simply goes to completion. Now, let's read the orange statement. I'm going to leave that there. If K is a number that's less than 1, what that means is at equilibrium, you're going to have less products than you have reactants, more reactants, higher concentration of reactants at equilibrium. And because of that, we can say, well, it's the reverse reaction that's favorable. The reverse reactions means you're taking your initial products and you're remaking reactants. Okay, so that corresponds to the orange portion of the arrow, where K is a number between 1 and 0.001, 10 to the minus 3, and you have more reactants than products present. Lastly, if K is way, way smaller than 1, less than 0.001, the forward reaction does not occur. You don't have any products at equilibrium. You have mostly all reactants. Or a very high concentration of reactants compared to a concentration of products. So that tells us the ratio, right? Do we have more products? Do we have more reactants? Are they pretty similar? If K is a number that's right around 1, then your concentration of your reactants and your products are going to be pretty similar. Not exactly the same, pretty similar. So this would be a great question if we could to have a poll, a Zoom poll, but since we're not on Zoom, I want you to pause the video as you want, or as you to have yourself kind of guess the answer, and then make your guess or your prediction, and then play and see if you get it right. But I want you to kind of try to think about these on your own. So here's our question. What conditions would you expect? What do I mean by that? The conditions mean what is the ratio of the concentration of products compared to the concentration of reactants. Okay? What kind of statement can you make the way we made up here, okay, about products and reactants? Do you have more products? Do you have more reactants? That's what I mean. What kind of conditions? How much products, how much reactants, how do they compare to each other? So what conditions would you expect to find at equilibrium for these reactions? Okay, so let's look at number 1. We have this reaction, hydrogen and oxygen make water, and K is 3.1 times 10 to the power, look at that, that's a huge exponent, 10 to the power of 81. 81 zeros after this. It's a massive, massive number, okay? Way bigger than Avogadro's number. So, if that's K, what does that correspond to? Think about these color-coded statements up here. Where on the arrow does that number for K fall? And what it means is that it falls in the purple region up here, okay? Which says that to be in the purple region, your K is much, much greater than 1. So here K is way, way bigger than 1. It's big, way, way bigger than 1,000. So what that means is that the forward reaction to make our products is the favorable reaction. And essentially it's going to go to completion. You're going to have no reactants, and you're going to have all products. All right, so that's number 1. Let's look at number 2. We have nitrogen and oxygen gas, and they make nitrogen monoxide. And here is your value of K, 4.7 times 10 to the minus 31. Here, K is much, much smaller than 1. What does that correspond to? That corresponds to the red section of the arrow, where it says forward reaction does not occur. Okay? So the forward reaction, the reverse reaction is the one that's favorable. The reverse reaction is favorable, And at equilibrium, you're going to have all products, no I'm writing this backwards. It's way too late. That's what that means. All reactants, no products. Because the value of K. Number 3, we have a K that equals 3.4. That's very, very close to 1. All right. Now it corresponds to this light blue region of the arrow. And what does light blue or blue say? Blue says when K is greater than 1, the concentration of products is greater than reactants, and the forward reaction is favorable. But here, just barely. So here, the forward reaction is favorable, but I'm going to write barely. Okay, so the concentration of products is greater than the concentration of reactants, but not by much. They in fact are kind of similar. So you can put that little squiggle underneath it to indicate that they're kind of similar, but barely the concentration of products is greater. Because K is a value that's very close to 1. It's between 1 and 1,000. So here's an example problem, a problem to practice or work with equilibrium. It says water and methane, which is carbon tetrahydride, react to form carbon monoxide and hydrogen gas. Write the balanced chemical reaction. So I suggest you pause the video, go ahead and do that, and then pick back up once you have that done to see if you get it right. I'm going to go ahead and do it. Water, H2O, plus carbon tetrahydride, CH4, react to make carbon monoxide and hydrogen gas. We know hydrogen is a diatomic molecule, so there we go. Now, we know water. I'm going to put the states of matter in, just in case we need it. Methane, I believe methane is gas. Carbon monoxide is a gas. Hydrogen is a gas. Write the equilibrium equation for the reaction. Okay, so if I'm writing my equilibrium equation, that's my equation for K. So K equals concentration of products, CO, raised to the, I didn't balance it. I wrote my equation, but I did not balance it. So to balance it, how do we best do that? We've got 6 hydrogens on the reactant side. We need 6 on the product side. And I think it's now balanced. 1 carbon on each side, 1 oxygen on each side. All right. So we would do CO raised to the power of its coefficient, which is just 1, times the concentration of hydrogen gas, H2, raised to the power of its coefficient. And on the bottom, I'm only going to put the concentration of CH4 raised to the power of its coefficient. I'm not going to put the concentration of water because it's a liquid. I'm only going to plug in gases or things that are aqueous. All right, so there's my equilibrium expression or equation for the reaction. I guess I should put my reversible arrow here too, if it's able to reach equilibrium. Now it says, if K is 2.5 times 10 to the power of 6, are the reactants or the products favored at equilibrium? Well, here's what I know. 2.5 times 10 to the power of 6, that is much, much greater than 1 or 1,000. If you look at this arrow, let me erase right here. Okay, that corresponds, 2.5 times 10 to the power of 6 is definitely in the purple region. What that means, are reactants or products favored at equilibrium? Because this is greater than 1 and 1,000 as well, it's greater than both of these numbers. That means products are favored. You're going to have way more products, mostly all products, no reactants. All right, well, that concludes our talk on equilibrium and how to calculate or write an expression for K, and then how to calculate K, and then make some statements about what that means regarding our conditions at equilibrium.